Hi everybody, welcome back to the Feynman technique. So today we're going to evaluate this integral that I'm calling the parameterized bivariate log-trig integral because it's parameterized, it has two things that are varying, and it has logarithms and trigonometric functions in it. So, how are we going to do this? Well, the first step is we're going to take a derivative with respect to a using the Leibniz rule for differentiation under the integral sign. All right. Um, basically what we do is we pass this derivative inside the integral and then take the partial with respect to a of the integrand. And this is what we end up with. All right, so we've currently got a mix of cosine and sine terms. So let's try to make some tangents out of this. Well, we could make a tangent out of this sine squared by multiplying it by secant squared or dividing it by cosine squared x. So let's do that to the top and bottom. And then you'll see these cosine terms are just going to cancel out. So this is what we end up with. And now the obvious substitution is that u is equal to tangent x, or dx is secant squared x, or du is secant squared x dx. Dx is du over secant squared x. But we can rewrite secant squared x as 1 plus tangent squared x. And since tangent is just u, we have dx is du over 1 plus u squared. And plugging that back in, and we end up getting this. All right, now that's not that bad to integrate. Well, first, actually, we need to replace our dx term. So let's replace our dx term, and now we have this. Now this is a little harder to integrate. We're going to have to break out partial fractions, but that's not that bad. So right now we have I prime of a is equal to this. So let's use partial fractions on our integrand. So we set it up like this, and then I'm not going to show the entire process of decomposing that, but this is what you get. You'll see that a is equal to this and b is equal to this. It's complicated, but it would make this video too long to show every single step of that, so I'm not going to do that. Plugging that back in, pulling all the stuff out, simplification, all that that nice algebra that we all love to do, and we end up with this. Okay. And these are both arctangent forms. These are very easy to evaluate. So again, I'm not going to show the steps there. If you want to pause the video and go through the steps, these are what they are. So basically, we just take the antiderivative, pull out the constants, evaluate the antiderivative at the bounds. This is what we end up getting. And then after simplification, we see that I prime of a is pi over a plus b. All right, so what we do is we're just going to call I prime of a derivative of I. So di is pi over a plus b dA. So let's go ahead and integrate both sides like that. And we get I in terms of a is equal to pi natural log of a plus b plus a function of b. Don't forget our original parameterized integral was a function of both a and b. So technically our constant of integration when we integrate this is going to be a function of b. So that's why we have our, typically this would just be plus c, but don't forget it's actually plus c of b. All right, well, in order to solve for c of b, we're going to need an initial condition. If we plug in b into our original parameterized integral, this is what we get. And then you'll notice that this b squared is going to factor out, and we'll just be left with cosine squared x plus sine squared x, which is 1. So here's the steps to do that. We factor out the b squared. We recognize the Pythagorean identity, and then we can bring out the 2 inside the natural log, and finally we have I of b is pi natural log b. Substituting that back into our equation, now we have pi natural log b is equal to this plus our c of b. using properties of logarithms, algebra, and all that good stuff. And we finally end up with C of B is equal to negative pi natural log 2. All right, so we plug that in, and we have our original I of A is equal to this. And finally, combining those two, we get our final answer for our integral, and it's just pi natural log of quantity A plus B over 2. All right, guys, hope you enjoyed that. We'll see you next time.